Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample consisting of 2.5 mole of perfect gas molecules with Cp, m is equal to 20.8 joule per mole Kelvin is initially at 240 kilopascal and 325 Kelvin. It undergoes reversible adiabatic expansion until its pressure reaches 150 kilopascal. Calculate the final volume and the final temperature and work done. So the question is telling us that we are dealing with a reversible adiabatic expansion process. So it's very, very important anytime you have a question in physical chemistry, thermodynamics, that you always know what process that you're dealing with, right? Or what process that you're given. Because you could be given an isobaric process, meaning constant pressure, an isothermal, constant temperature, or an adiabatic, which is a process where there's no heat transfer. So this would help you in knowing what formulas you're supposed to use in calculating questions and what concepts you're supposed to put at the back of your mind while you're dealing with a question, right? So, next thing you do, of course, after you've determined and become familiar with what the question is asking you, is for you to write out your parameters. We have the number of moles to be 2.5 mole. We have the Cp, m, which is just the molar heat capacity at constant pressure to be 20.8 joule per mole Kelvin. We have the initial pressure to be 240 kilopascal. We have the initial temperature, because they said initially at 240 kilopascal and 325 Kelvin. So T initial is just 325 Kelvin. They told us that it undergoes reversible adiabatic expansions until its pressure reaches. So there's a decrease in pressure. So P final becomes 150 kilopascal. So we are asked to find the final volume, okay, the final temperature, as well as the work done, the adiabatic work done. So these three is what we're actually solving for in this question. Of course, the work has begun. So the first thing you have to note is that adiabatic expansion problems are usually dealing with perfect gas equations or perfect gas molecules. So you're going to have to apply the perfect gas equation here because we're given the P initial, we're given the P final, we're given T initial, we're not given the T final or the V final or even the V initial. And because it's an adiabatic work done process, we cannot just jump into things. So to determine the V final, right, we would actually need the V initial. The reason is because anytime you're given an adiabatic expansion process and you're asked to determine the V final, you have to use this formula, which is just P final multiplied by V final raised to the power of gamma is equal to P initial times V initial raised to the power of gamma. So that's why we have the P final, we have the P initial. We don't have the V initial, and we're asked to determine the V final. So we actually have to determine the V initial. So to do that, we have to use our basic understanding of the perfect gas law or the perfect gas formula, which is P initial times V initial is equal to nRT initial. By doing an adiabatic problem, you have the final volume, sorry, and the initial volume different, the final pressure and the initial pressure different, the final temperature and the initial temperature different, meaning you don't have any constant pressure, constant volume, or constant temperature. Every initial value and final value is going to vary from one another. The only thing that is constant is the fact that there's no heat transfer. So anyways, yeah, so this is basically what you have. So we determine the V initial to just be nRT initial divided by P initial. We have the number of moles to be 2.5 mole. We have what do you call it? We have our R to be 8.3145 joule per mole Kelvin, which I can just say Newton meter divided by mole Kelvin because joule is equal to Newton meter. Anyways, you see the reason why I did not write joules in a second. Times temperature. So T initial is, what was T initial again? Our T initial was 325 Kelvin. So 325 Kelvin divided by pressure, which is just 240 kilopascal, right? So that would be 240 kilo as in times 10 to the power of 3, and then pascal, which is just simply Newton per meter squared. So pascal is just simply Newton per meter square, meaning it's a unit for pressure, and pressure is just force over area. So that's basically how you got it. That's the more reason why I did not keep our this thing joules, put our gas constant in joules per mole Kelvin, but instead in Newton per meter, sorry, in Newton meter. So yeah, you need to like think about things like this anytime you're doing a physical chemistry thermodynamics question. So you did, of course, now it's time to cancel out the units. To cancel out mole, cancel out Kelvin, cancel out Kelvin, cancel out Newton, cancel out Newton. So V initial just simply is 2.5 times 8.3145 times 325 divided by 240 times 10 to the power of 3. Making sure to put this information. So let me just rewrite it times 8.3145 times 325 divided by 240 times 10 to the power of 3. And then you've got meters here. And then, of course, you have divided by 1 over meter squared. So times 1 over meter squared. So when you have all of this information here, right here, right, I'm going to input all of this information in a calculator. So I end up with V initial is just simply this information in a calculator. I end up getting 0.2815, and then you've got meter divided by 1 over meter squared, which is just simply meter divided by 1 over meter squared. If I put this calculation beside here, that would just be meter times meter squared over 1, just meter cube, which is a perfect unit because we're dealing with volume. So our volume, initial volume, is just simply going to be, V initial is just simply going to be 0.02815 meter cube. So this is basically the answer. So this is our V initial. So we've determined our V initial. Now we can determine our V final and actually answer the first part of this question. So V final is what we are asked to determine. So rewriting this formula here, I apologize, what's going on? So rewriting this formula, P final multiplied by V final. So rewriting the formula, I have P final times V final raised to the power of gamma is equal to P initial times V initial raised to the power of gamma. Before I go on to solve this question, please, for the sake of God, I beg you, make sure you pay attention. You may actually have to watch this video more than once, because it's not hard. It just has a lot of elements playing in the question. So you have to pay as much attention as possible. So now we have our P final. We know our P final to be going back. I just want to write everything down so we don't have to keep going back and forth. So that'll be 150 kilopascal. P initial is 240 kilopascal. So P final, 150 kilopascal. P initial, 240 kilopascal. And then V initial, of course, 0.02815 meter cube. So yeah, we have all what we need now to determine our V final, or almost all what we need. Now, you may be wondering, okay, what's going on here? We want to determine our question, but then we have a situation here. We have the variable gamma. What is gamma? What is gamma? Gamma is just simply the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. That is simply what gamma is. And the molar heat capacity at constant pressure has been given to us, but we don't know the molar heat capacity at constant volume. Well, we this is where you would enjoy physical chemistry. Remember that the molar heat capacity at constant pressure minus the molar heat capacity at constant volume is just equal to R. It is R that is the relationship between the constant pressure. Sorry, is R that is the relationship or that connects the molar heat capacity at constant pressure of a gas to the molar heat capacity at constant volume of the same gas. So to determine this, we can just simply define, so we can just simply determine CV comma M to just be CP comma M minus R. So CV comma M is just simply 20.8 joule per mole Kelvin minus 8.3145 joule per mole Kelvin. CV comma M is just 12.486 joule per mole Kelvin. So yeah, that's basically it. So gamma again is, let's determine gamma here. So gamma is just simply CP comma M divided by CV comma M. So that's just simply CP comma M. We know that to be 20.8 joule per mole Kelvin divided by CV comma M, which is just 12.486 joule per mole Kelvin. So divided by 12.486 joule per mole Kelvin. Cancel out the joules, the mole Kelvin, joule, mole Kelvin. So gamma is just simply 20.8 divided by 12.486, which is just 1.666. So that is basically it. Now we have done the work. We have determined gamma, and now we can finally find the final volume. So rewriting this equation, again, we just keep rewriting equation. Honestly, that's just how this question is. Anytime you're dealing with adiabatic expansion problems, just be ready to use your brain and to use brain power and to think of like multiple factors at the same time. Anyways, so you have P final, V final, gamma is equal to P initial, V initial, gamma. So V final, gamma is just simply, if we make that the subject of formula, we have P initial, V initial, gamma divided by P final. Yeah. And then, of course, you're going to be wondering, maybe we can make this easier. So we can just simply raise both the information on the left side of the equation and the right side of the equation, raised to the power of 1 over gamma. 1 over gamma. And I'm going to tell you the reason why we're doing that soon. For those of you who are avid mathematicians, then you of course already know the reason why I'm doing it, but you're going to see the importance in a second. So you have V final, gamma multiplied by 1 over gamma is equal to P initial divided by P final raised to the power of 1 over gamma, okay, multiplied by V initial gamma, right, times 1 over gamma. So the reason why I did this is to make our work easier, so we can like cancel out some of the gammas in our question. So yeah, that's just basically why I'm doing it. So to make sure that we have our work easier to digest. So rewriting the equation, finally, we have V final is equal to P initial divided by P final raised to the power of 1 over gamma times V initial. So this is the equation that we're going to finally use and substitute. So yeah, that's it. So we have V final is just the P initial, going back up. Our P initial is 240 kilopascal. So that would be 240 kilopascal divided by P final, 150 kilopascal. So 150 kilopascal raised to the power of gamma, which is just simply 1.666. So raised to the power of 1.666 times V initial, which is just simply 0.02815 times 0. Oh, I apologize. I actually just saw a mistake. It's not raised to the power of gamma, raised to the power of 1 over gamma. So I apologize. Raised to the power of 1 divided by 1.666. So yeah, that's it. That's how it's supposed to be, times what V initial is, which is just 0.02815 meter cube. So cancel out the kilopascal, cancel out the kilopascal. So you end up with 240 divided by 150, which is just simply 1.6, and then 1.6 raised to the power of 1 over 1.666. Raised to the power of 1 by 1.666. Anyways, that's it. Times 0.02815 meter cube. So putting this part of the information in the calculator, we end up with 1.32591. Okay, so V final is equal to that times 0.02815 meter cube. So yeah, that's it. So when you multiply both of the information, you have 1.32591 times 0.02815, you end up with 0.03734 meter cube. So that is basically it. Now, you may be wondering, okay, we've done it, we've gotten the answer, but we're dealing with a chemistry question, so we can't just put this and say, oh yeah, we're done, we've gotten the answer. You actually have to put in the proper number of significant figures. So I'm going to go back to where we're giving the parameters, and I'm going to see the number of significant figures that we're given in the question. I'm just going to put my answer for volume in two significant figures. And the reason why I'm doing that is mainly because if you look at the initial volume, the lowest we had the number of moles to be 2.5 moles. And in the rule in science is for you to use the lowest number of significant figures that you use in calculation of the problem. So V initial is actually the final answer for V is going to be in two significant figures. And of course, that applies to V final as well. So our V final is just simply going to be approximately 0.037 meter cube. So we have successfully determined the final volume. Now we have to determine the final temperature. So the first thing you have to do whenever you're determining the final temperature is for you to use the formula for determining final pressure in an adiabatic expansion. So the formula is V initial times T initial raised to the power of C is equal to V final times T final raised to the power of C, where C is actually equal to the molar heat capacity at constant volume divided by R, which is the gas constant. So basically, here we have the V initial as well as the V final, which we solved for. We have the T initial because we're given that in the question, and then we're asked to determine the T final. So before we go on ahead, we have all the parameters that we need in order to solve except for the value for CV, comma M. So it's important for you to know that CV, comma M, which we have determined, right, when we did 20.8 joules per mole Kelvin minus 8.3145. So we know our CV, comma M to be 12.486 joule per mole Kelvin. So we have 12.486 joule per mole Kelvin divided by gas constant, which we just know to be 8.3145 joule per mole Kelvin. Of course, you divide the units and cancel out the units. So you just cancel out the joules, the mole, the Kelvin, the mole, the Kelvin. So C becomes 12.486 divided by 8.3145, and that is just simply 1.502. So that is basically the work. Now, before we go on ahead, we can now basically substitute. But before substituting, we have to make sure we put all our this equation right here in the proper subject of formula. Meaning we're going to write it in terms of T final. So T final is the power of C. Let's not forget that is V initial times T initial raised to the power of C divided by V final. So that's just simply T final raised to the power of C is equal to V initial, okay, divided by V final times T initial raised to the power of C. Now we have what we need, but I'm going to try and manipulate this formula further so that it's easier for us to be able to properly work on this question. And by manipulating the answer, sorry, by manipulating the formula further, we'd have to multiply both sides of this equation by, or just not multiply, but raise both sides of the equation to 1 over C. So we're going to be using information on our knowledge of powers in mathematics. So when we raise both sides to the power of 1 over C, we end up getting TC, T raised to the power of C, times 1 over C is equal to V initial divided by V final raised to the power of 1 over C, okay, times T initial raised to the power of C times 1 over C. So what that would look like is to cancel out the C values here, cancel out the C values here. So this way, we end up having our work in a way that is easily digestible and it's easy for us to calculate when we substitute, because it becomes a lot more complicated if we have so many powers in comparison to having less powers to work with, right? So we have T final, because we've canceled out the C, is just going to simply be V initial divided by V final raised to the power of 1 over C times T initial. So this is basically the new formula. And of course, to determine the final temperature, we just simply substitute. So we have V initial to be 0.02815 meter cube. So that would be T final is just simply 0.02815 meter cube divided by V final, which we calculated, which is just simply 0.037324. I'm not going to use the approximate value for V final because whenever you're still calculating, you're not supposed to use the approximate value. Instead, you're supposed to use as much of the raw data or as much of the raw value as possible. So I'm going to substitute 0.037324. So 0.03724 meter cube. All of that raised to the power of 1 over C. So that's 1 divided by C is just, what is C again? 1.502. So 1 divided by 1.502 times T initial, which is just 325 Kelvin, right? T initial, which we've written out all of that. At the top here, 325 Kelvin. So I'm going to substitute that. Yeah. So multiply by 325 Kelvin. So we cancel out the meter cube, cancel out the meter cube. So T final would just be 0.02815 divided by 0.037324. That's just simply 0.75421. And then 1 divided by 1.502 is just raised to the power of 0.666. Okay, times 325 Kelvin. So T final is equal to this information right here, which is just 0.75421 raised to the power of 0.666. So that would be 0.8287239 times 325 Kelvin. So T final is just 269.335 Kelvin. So this is basically the final answer for temperature. So the final temperature is 269.335 Kelvin. But you know for sure you are a chemist, a scientist. You know you're not going to leave it. We're going to leave it in the proper number of significant figures. And if we look at the initial temperature, we see that the value for initial temperature is 325, meaning it's in 3 sig figs. So we're going to put our final answer in 3 sig figs. So the T final is actually going to be T final is approximately 269 Kelvin. So this is basically this is basically the answer. Final temperature is 269 Kelvin. Now we have determined the final volume. We have also successfully determined the final temperature. Now we have to determine the work done, the adiabatic work done. So calculating the adiabatic work done, we have to first of all note again, since we're dealing with an adiabatic expansion problem, you know that the adiabatic work done is just simply CV, comma M times the number of moles times the change in temperature. So CV, comma M meaning the molar heat capacity at constant volumes times the number of moles times the change in temperature. So the adiabatic work done is just simply CV, comma M is 12. Okay, we've determined that 486 joule per mole Kelvin. Okay, times 2.5 mole times the change in temperature, which is just simply T final minus T initial. As usual, I'm not going to use the approximate value for T final, so I'm just going to have 269.335 Kelvin minus T initial, which is just simply 325 Kelvin. So the adiabatic work done is just cancel mole, 12.486 joules times 2.5 times, so 12.486 joules times 2.5 times 269.335 Kelvin minus 325 Kelvin is just simply negative 55.665 Kelvin. So adiabatic work done is just going to be us multiplying all of this, right? This one is actually joule per Kelvin. I apologize. So you cancel out the Kelvin here, you cancel out the Kelvin here. So the adiabatic work done ends up becoming all of this information. You put in your calculator, you get negative 1,737.583 joules. And again, we don't forget we are chemists. Because we are chemists, we have to make sure we put in the proper number of significant figures. So if you look at our work, we see that when we're yielding this calculation, we used 12.486. So this is the number of significant figures, 5 significant figures. We have this in 2 sig figs, and we have this one normally in 3 sig figs. So we have to put our answer in the lowest number of significant figures, which is 2 sig figs. So the adiabatic work done is going to be approximately negative 1.7 times 10 raised to the power of 3 joules, or negative 1.7, not 1.7, sorry, negative 1.7 kilojoules. So this is the answer. So adiabatic work done is approximately negative 1.7 kilojoules, or negative 1.7 times 10 to the power of 3 joules. So this is the end of this particular video. If you have any questions, please put in the comment section. If you have any concerns or suggestions, also put in the comment section. For those of you who don't know, this is one of the questions I'm doing from the Physical Chemistry Atkins 11 edition textbook. And if you look at the description box, you're going to see a link to buy the book, as well as the link to the playlist where I've done over 90 questions from this book. So make sure you keep watching and make sure you like and subscribe. I also wanted to mention that if you're a student who's struggling in any of your STEM related courses, whether you're in middle school, high school, college, I am the tutor for you. I help students succeed in all their STEM related courses, whether you're in middle school, high school, and college. I also help mentor students as they navigate their academic life. So if you're trying and striving to succeed, make sure you email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.